research and innovation actions, which are funded by the 2.0 partnership. You don't see them yet, but they are here with me. We have 6 speakers. They are going to tell us about their projects, and I'm going to introduce them one by one as we go along with the session. And then we have also here with us Mr. Bein, Thilo. So he's from Fraunhofer. He is also one of the vice chairmen of the executive board of the 2.0 partnership. And he will help us understanding what are the achievements which has been done so far in this area related to materials, lightweighting for the automotive industry. And he will also share with us his thoughts with respect to what remain to be done in this domain. So the 6 projects that are going to be presented are Fatigue4Light, ALMA, Revolution, LEVIS, and FLAMINGo. So these are all ongoing projects. So they started in the beginning of 2021, and they will end up in about 1 year, apart from FLAMINGo, which is a little bit longer, and it will finish in 2025. They are all working on the same thing. They are all working on lighter materials compared to the solutions that already exist on the market. And of course, the reason is for improving the efficiency of the vehicles, improving the range, and we know how this is important for electric vehicles. So the projects are going to talk about the components, the parts of the vehicle that they are working on. They will present the materials that they are using or that they are developing. And the time is available is not that much, but they will also explain how the solutions that they are developing are technically sound, economically sustainable, and also, economically viable and sustainable. And then we are supposed to have a 6 project presented upscale, but I don't see the speaker here.
I will look fine.
Okay, so there should be also a 6 project presented upscale. This is a project that finished last year. And it's slightly different. So there is about digitalization, and in particular is about the use of artificial intelligence and the application of artificial intelligence for with respect to the production processes. And in this case is to reduce the time which is necessary to develop new complex electrified platforms. So this is in a nutshell the content of the presentation for today. If you have questions, and I really hope that you will have, there will be a microphone going around. So we're going to allow some time at the end of each presentation. So depending also on how we progress, but okay, there will be time for the presentation. Then at the very end, there will be the final discussion that will be moderated by Mr. Bein. And we can take hopefully some questions also at that time. Okay, so without any further ado, I propose that we start with the first speaker. So the first speaker is Mr. Jimenez Sergio. He is the coordinator of project Fatigue4Light. He is a researcher at CINEA and works also as an associate lecturer in structural analysis in mechanics at UPC in Spain. So if you're ready, Mr. Jimenez, the floor is yours.
It will work, okay. Nice to know. Okay, and you said that I should be clicking this. Now, everything works. Thank you, thank you. Thank you, Eric, for your kind presentation. As Eric already told you, I'm Sergio Jimenez. I'm the coordinator of the Fatigue4Light project. And the main aim that I have for today's presentation is to introduce you this project and share with you some of the results that we've already obtained on the project. In order to do so, I prepared this presentation here, following this structure, in which I will be first presenting you basics of the Fatigue4Light project. Then I will also introduce you the consortium that is working on the project and which are the main objectives that we're trying to successfully fulfill along the project. Then I will move towards the presentation of this section, which is called Project Status, in which I will introduce you the work that we've been doing all along this period of time since we start the project. And then finally, I will introduce some of the expected impacts coming from the consecution of the Fatigue4Light project. Okay. This project is an H2020 project funded under the topic of advanced light materials and their production processes for automotive applications. As already Eric mentioned, this is a 3-year project, and we are now initiating our last year in the project, and it's being coordinated by the research group from Barcelona, CINEA. A total of 13 partners is working on the project, coming from Spain, France, Italy, and Sweden. And you can see here which is the division between research institutions, universities, industrial companies, and standardization bodies that are working on the project right now. Here I have summarized the main objectives that we are pursuing in the Fatigue4Light, but rather than explaining them by myself, I prefer to share with you this video that we've prepared on the Fatigue4Light for dissemination purposes.
Did you know that the chassis of an electric vehicle accounts for 50% of its weight? What if we could reduce the weight and thus increase the vehicle range while contributing to a more sustainable mobility? Lightweight materials have been around for some time, with great potential in reducing the vehicle's weight without compromising safety. However, they introduce significant challenges related to part design and performance.
It's working on the lab.
Select the optimal materials for lighter vehicle chassis and reduce the testing time for new materials. Based on eco-design, the Fatigue
Maybe it's not a good option.
mental methodologies to select the optimal materials for lighter vehicle chassis and reduce the testing time for new materials. Based on eco-design and circular economy values, Fatigue4Light aims to boost the use of lightweight materials adapted to the chassis parts of electric vehicles, enhancing weight reduction while increasing vehicle safety. As one of the Fatigue4Light takes a step to make advancements in building a zero-emission future, while simultaneously minimizing production losses and meeting the industry needs. To find out more about the Fatigue4Light project, visit our website www.fatigue4light.eu or follow us on social media.
Okay, anyway, basically the main idea is to achieve a weight reduction at the vehicle, at the electric vehicle level, and we pretend to achieve this result by using new materials and also by developing new numerical technologies and new tests, experimental tests. This is the main idea of the project. If you want to see the complete video, you can visit our YouTube page and you will find it there, or even in our web page, you will find the link to the video, okay? Then, now that you have more or less an idea of which are the objectives of the project and with what are we pretending to do on the project, and before showing you which are the results that we've been obtaining all along the project, let me just share with you which is the approach that we've been following along the project. The Fatigue4Light, it's a 3-step project in which we first of all focus on the study of the materials that we will be using to achieve our objectives. So we work at following a material perspective, and we focus all the efforts on characterizing the properties of those materials. Then, once we've done that, we move towards including now the manufacturing effects that would appear for sure on the final pieces of the vehicle. And in order to do so, we move towards this lab demonstrator perspective. And we there simulate and perform some experimental tests on these, let's say, more advanced samples, which include the information obtained previously, but now we add these new challenges coming from the manufacturing processes, streaming, punching, and forming, for example. And then once we got all this knowledge, we apply it in order to verify that we can achieve our objectives by applying all these techniques and this knowledge on these final components specimens. This is just one example. And by checking that we are fulfilling our objectives on these specimens here, on these components, we then scale the results to the chassis level. And all this work, we do all this work following through research lines. We follow a life cycle assessment perspective. We also do experimental work, and also we dedicate some efforts for numerical modeling. And the results that I will be presenting are coming from the work done for each of these three research lines. So regarding the life cycle assessment, basically what we've done here is defining an eco-design approach that we used as a decision maker to select the materials to be used, and also to define the design of the chassis parts. And from this study, we finally end up by selecting these materials here, which mainly are high-strength steels, manganese steels, stainless steel, aluminium solutions, and also hybrid solutions, including GFRP and aluminium. And we also decide at this step which were these geometries, these components that will be studied on this last part of the project, which are this low control arm, this shocking tower, this beam here, and these wheels. Now, moving towards the experimental work, I've only included here two of the main outcomes of the project, which are related with this work here, which is basically the definition or the proposal of new experiments, new rapid fatigue tests, and we've used them to characterize our materials, and we validate them comparing with the conventional techniques. And we finally conclude that we have achieved a really significant reduction in time that for sure will be really interesting for industry. And I'm also including here the big amount of work, of effort that we've dedicated to the study of these manufacturing effects on the effects that these manufacturing processes have on the materials that we are studying. And we here have studied punching, trimming, forming, and welding. Okay. And we've seen which is the effect over the fatigue response of the materials that we are studying. And finally here, what I'm presenting is the work that we've done with respect to numerical modeling. On the Fatigue4Light project, basically what we've done is proposing a new numerical methodology to study these fatigue processes. And what I've included in this image is a brief summary of the steps that we've been following up to now in order to first generate the methodology and then apply it, and also improve it if necessary. So the first thing that we've done is comparison with respect the available widely used commercial techniques for the study of fatigue processes. Then we applied this methodology on the study of advanced fatigue failures, including load sequence effect, residual strength analysis, and overload phenomenon. And right now we are finishing an extension of this methodology in order to include these manufacturing effects that we also studied experimentally, and I commented previously. Here you can see just two examples of one part of the punching modeling, and also of the forming modeling process. Okay. And before going to this section of the impacts, I would like to comment some of the direct outcomes which can be quantified that have already come from the Fatigue4Light project. In terms of participation in congresses sessions, published papers, we've already published 4 papers in peer review journals. We've also worked on preparing dissemination material in terms of a website, the video that you've seen, working on social media and flyer. I have the flyers there, and if you want, you can ask me for one, or I can distribute it now. And we are also currently working on the standardization process of the experimental techniques that I previously mentioned. And I've also wanted to mention here our participation in this enlightened electric vehicles cluster that we used mainly to share in a more effective way with the whole community all the results and all the knowledge that we are obtaining from this set of sister projects that Eric, that are presenting today on this session. And basically, up to now, what we've been doing is participating in joint seminars and congresses sessions. And just to finish now, I would like to briefly talk about the impacts that should be expected from the Fatigue4Light project, which should be, of course, related with the work that we are doing that I've already presented to you, related with the use of new materials and the smart design that I let's say, mentioned, but not presented in really depth. We should expect the weight reduction, which is the objective, the main objective of the project. Also, considering the use of these numerical techniques and the new experimental tools proposed from the project, we should expect an increase of efficiency in vehicle development. I've already mentioned, we've been working on the fatigue assessment, and we have a work package dedicated to sensoring. And from this work, we expect to assess the structural integrity procedures and efficient repair reuse techniques. And finally, related with the eco-design perspective that we're following in the Fatigue4Light project, we will finally be able to generate an effective solution for reuse, recycling, and recovery of material. My last slide now is the connection of these impacts with the European policy objectives. And this allows me to conclude that the Fatigue4Light project will contribute to generate a more competitive, smarter, greener, connected, and sustainable Europe. Thank you very much, and I will be glad to answer all your questions.
Okay, thank you very much, Mr. Jimenez. Are there any questions from the audience or from you, Thilo? Do you have any questions?
Just waiting for the audience.
Yeah.
If not, I have two questions.
Okay.
One is a scientific one. The acceleration of the obtaining the SN curve, the strain
one
rate. Is it similar to the incremental step test? What?
Not sure. We have published papers for these methodologies, so maybe you can check there. This work has been conducted by Eureka. Sorry. I was saying that I'm not sure about the frequencies that they use here. We have published papers for these methodologies, so you can check there which are the frequencies that they used. But in fact here, as far as I know, it's not that, I mean, for the thermal control, yes, for sure it is important, the frequency. But what they expect there is to reach this stable condition here, in which the temperature is not evolving, okay? In which you reach this steady state there. But here you are not checking the temperature. You are just checking the evolution of the strength of the material. And I'm not that sure that they pretend to go on a really high frequencies there.
Okay, I will check with the the second question related to the end-of-life strategies. You mentioned that you have recycling concepts and end-of-life concept. Can you elaborate a little bit more on that?
Okay, I'm not the expert on that. Eurecat is working on that, and also RISE is working on that. Again, we have this deliverable, which is public and available on the website. As far as I know, what we've been developing is the guidance that we should be following. And now we've shared, well, now at the very beginning, and now we are ensuring that all the industrial partners which are involved in building these components here are following this guidance. But I'm not really sure of which are the specific points that we are following there.
Okay, thanks.
Hello, my name is Horst Flügel from AVL. You mentioned at the beginning that 50% of the car's weight is the chassis.
Mm-hmm.
I recently saw a video from Tesla, the pickup truck actually, with stainless steel. You might know that.
Not sure.
Okay, so the concept there is to use stainless steel
Okay.
and special forming techniques, avoid painting because it's not necessary.
Mm-hmm.
Having already the structure stiffness of the chassis. I don't know if you're all aware of that concept. But what about such concepts? Use stainless steel for the chassis.
It's, I mean, we are studying also this stainless steel here, and we are shifting for some of these components towards the use of this stainless steel. As far as I know, I'm not sure if this can be directly applied to big pieces, because here what we are doing is just working at the component level, and we are shifting between materials which are more or less which resemble in terms of strength properties and also fatigue properties, and even we achieve better responses from those materials. But we are not considering only using this stainless steel solution. We are considering other options too.
One more.
And who was first?
The lady.
You have my email at the, well, here. So if you have more questions, because I will be leaving more or less by the on the third presentation. So if you have more questions, you can send me also an email there. Okay.
From Green Innovation and previously at Renault. I know that for sure, because I was in charge, the adoption by project of lightweight solution is on basis of cost.
Okay.
You have a cost threshold for a kilo earned. So I haven't seen any indication about cost, unless I am mistaken.
Yeah, I mean, even the weight, all we've done, I mean, all the predictions in terms of real weight savings and the corresponding economic savings will be done on this final part. All we've done up to now is a prevision at the very beginning of the project, in which we estimate the weight being that we can reduce at the chassis level. But I can find out which is the cost value that we are managing, and I can share it with you for sure.
Okay, thank you very much, Mr. Jimenez, for the presentation. In any case, it's actually maybe, as I said, cost is certainly part of the project. So today I agree there was nothing that was shown on that level, but it's something which is considered, and it should come. Is already there are already things which has been done as part of the project, delivery which are available. So the time is we are on a time constraint. So this was not presented, but maybe if you can discuss later on with Mr. Jimenez. So we are going to move to the second presentation. So this is about project ALMA. So Ms. Ledo Raquel is the speaker. She's head of materials innovation at CTAG, which is the Automotive Technology Center of Galicia in Spain. So if you are ready, Ms. Ledo, the floor is now yours.
Okay, thank you very much for your kind words. Thank you very much for your attendance. Sorry, because I move. Thank you for your attendance, and thank you for this opportunity to talk about ALMA. ALMA is a consortium of 9 partners from 4 countries. We have 5 market-oriented companies, 3 big ones, ArcelorMittal, Ford, and BAT, 2 SMEs, Rescol and Interspec, 3 RTOs, CTAG, where I work, Fraunhofer and TNO, and 1 international association. We have around 4 million of budget, and we started this project in February 2021. So that means that we have just started we have 3 years of duration, so we have just started the last year of the project. So at this point, let me share with you one reflection. Here we have a photo of a pregnant woman. When a woman is pregnant, she has a very big challenge, a very big objective during 9 months, and this objective is to guarantee the safety of the baby. This is the main challenge. So there are another objectives. Maybe we can talk about avoid to gain weight because it's not good for the woman and not good for the baby. But the big challenge is to maintain the protection of this baby. When we talk about cars, it's exactly the same. Our first challenge, our first goal is to guarantee the safety of the occupants. So ALMA is about lightweight, of course, but we can't forget what is the main point, and the main point is to guarantee the safety of the passengers. If we talk about electric vehicles, we have 2 types of passengers. We have people, but we have another little passenger that is the battery. So we have 2 types of baby, and we have to protect both of them. So I always would like to mention this because it's something that is really important. But I take before, ALMA is about lightweighting. So the first, if we talk about specific objectives, we can talk about reduce the weight of the vehicle structure. In this case, we are focused in the body structure, in the body in white. We are talking about incorporating new eco-design strategies because we have to think in meeting the requirements, but also we have to think in what is going when we arrive at the end of the life. So from the first beginning, we have to think about this. At the end, the global objective is to decrease the environmental impact of electric vehicles at global level. And of course, when people was talking about this, we are in the automotive sector, so all the technologies, all the solutions we are presenting should be affordable. For us, the cost and the safety are the 2 main points. So this is our approach, but I'm going point by point. First step. Our starting point was taking the Ford Mondeo. The Ford Mondeo for a a standard vehicle, I mean an internal combustion engine vehicle. So the first point was to translate this structure to an electric structure. When we obtain this electric structure, we start to redesign. So CTAG, my company, work in this point about redesigning all the structure. And there are three main points. The first one is the best material for the best location. We have to know if we need more rigidity, if we need more energy absorption. So it's really important, the best material in the best location. Then, if we can integrate functions, we should do. I mean, we are going to work with new innovative materials. And in some cases, we will be allowed to integrate 1, 2, 3, 4 parts in one only part. So this is important also. And I mentioned before, we are redesigning this structure for meeting the requirements, but also thinking in the future, also thinking in the end of the life, also thinking in the recyclability. So I repeat, CETAC was in charge of the redesign of the structure, and our colleagues from TNO has developed a tool, an BEPSIM tool, that carry out with the LCI and LCC. Also, costs are important for us. If we talk about innovative materials, in this case, in ALMA, we are working with two types of materials. Steels, high-performance steels, of course, and SMC, shield material compounds, and in both cases, devoted to lightweight, of course. In the case of steel, ArcelorMittal is responsible for that. We are working with three new steels. One is a sandwich of steel and plastic. The other is a low-density steel. And the last one is a high-performance steel, an HSS steel. So this allows us to decrease the thickness of some pieces, some parts. And the other important point is the possibility to integrate functions, as I mentioned before. In this point, we have changed 165 parts in steel. And the other material, SMC, is based in resin with random glass fiber. And we are just working with some textiles, some glass fiber textile, to increase the rigidity of some parts. And our goal is to develop the battery cover and the dash panel. Well, new innovative materials, new design, but we have to be sure that we are meeting the requirements of the car. So our colleagues from Ford has carried out all the tests and all the simulations needed to be sure that all the crash behavior is right and we are meeting these requirements. And our colleagues from Fraunhofer has carried out the activities related to the modeling and the preparation of the material cars of these new materials. And finally, in parallel, the SMEs, Rescol and InnerSpec, has worked in two different technologies. One is related with the adhesive. Rescol has developed the bondable adhesive that is activated by temperature. That means that with this adhesive, we are able to join steel and SMC materials, and at the end of the life, we apply high temperature. High temperature means 250 degrees, more or less, and we are able to easily disassemble the parts. And in the case of health monitoring, it's a technology based on ultrasounds that allow us to identify the status of the component. So when we reach this end of life, we are able to decide if the component is right or not, and we can reuse or not. So this is the work we have carried out during these 2 years. In the last year, we have to finish some technical tasks. We are going to focus also in the manufacturing of some parts to be sure that the technical feasibility is possible. and to be sure that all the results we have obtained at simulation level are right. So we are going to develop 2 or 3 demonstrators, 1 or 2 in steel and the other in SMC. But this last year, we will be always focused on sharing the results and to communicate the results. My colleague Sergio has talked about before. We have a cluster and light clusters where LEVIS, FLAMINGo, Revolution, Fatigue4Light, and ALMA are collaborating, and our idea is during this last year to promote more activities, more collaborative activities to communicate properly our projects. And all this is with the support of the Horizon Buster. And if we talk about the important and the more important, what is the impact of our project. So I would like to highlight 3 points. The first one is, I mentioned before, the BEPSIN tool. The BEPSIN tool is a tool that is available at our website and allow to the designers to identify in an easy way what is the best solution, the best material and the best design for a component in terms of LCA and LCC. One question that we receive usually is what is the difference, or what is the difference between BEPSIN and other tools, Sigma Pro, Gavi, etc. And the answer is easy. BEPSIN is not supposed, you don't supposed to be an expert in LCA and LCC. It's not needed. BEPSIN is focused on designers. So it's a easy way, it's really easy to use it and to have the first results to decide what is better or not. The second point, is about material cars. Our colleagues from Fraunhofer has developed a new methodology to develop these material cars for new materials, and they are able to reduce the test they need about 50%. So that means that for new cars, for new project cars, we are going to reduce the time and obviously the money we need. And the last point is about the innovative materials. These innovative materials allow us to decrease the thickness of the parts and to integrate. I repeat once again, it's really, really important to integrate different components. So we will be less manufacturing tools, less time of production, etc. So all this translates in this point. We have reached a lightweighting about 23% concerning the base of ALMA. The big companies in this project, Ford and ArcelorMittal, are now planning the launch of the new products, the launch of these new steels, and the launch of new electric vehicles. Ford estimates that around 2 million electric vehicles will be produced by 2026 and represents more or less half of global volume by 2030. And the results we are obtaining here in ALMA will be present in these new cars. So I have now...
With the state of our planet's climate and fuel prices spiraling upwards, it's crucial to make electric vehicles more competitive against gasoline and diesel options. Range is still a key issue for battery vehicles, with long charge times and sparse recharging stations complicating the matter. With bigger batteries out of the question, lighter vehicles are the solution. The ALMA project is a multidisciplinary group of 9 partners from across Europe, all united under the same objective: to make electric cars more lightweight, efficient and sustainable through an eco-design approach that uses new advanced materials. The project will improve the sustainability of vehicles by addressing each of the circular strategies. Performance on the road will be improved through innovative lightweight materials, thereby enhancing range and reducing energy consumption. Lifespan of the vehicles will be increased through health monitoring with sensors that detect damage and parts in need of maintenance before a critical failure. End-of-life scenarios will be optimized by ensuring recyclability of materials and debondable adhesives that can be activated to allow easy disassembly. The consortium has already achieved a 23% weight reduction compared to the baseline, reducing total weight by 200 kilos. This saves 240 kilowatt hours of energy and 84 euros due to lower consumption on a yearly basis. The vehicle's range is expected to increase up to 6%. To help achieve these results, the ALMA project has developed BevSim, a life cycle analysis tool for battery electric vehicles. Many ideas and materials can be tested much faster in simulations, saving a lot of time and money. ALMA, revolutionizing the automotive and transportation sectors through eco-design principles.
So it's all from my part. Thank you very much to the Commission by funding this project, obviously, and thank you for your attention.
Okay. Thank you very much, Ms. Ledo. So we have 5 minutes for questions. There.
Yes.
I can speak louder.
As yesterday, we have online participants.
This is for the previous presentation, for this presentation, and for the next 3 presentations,
Okay.
adding in their title, lightweight, lightweight. So, in 2020, Tesla started gigacasting, and they are introducing 10 to 15% higher weight than conventional steel making, and they are disrupting completely the automotive world. Okay, that's the point. And they are also disrupting the steel makers. Okay, 10 to 15% higher weight. Okay, weight is not the issue for Tesla, unless you consider Tesla a secondary player in electromobility. For them, speed is everything. Investment, your initial investment, is the main issue for all OEM today. But speed of production, for most models that they develop at Tesla, it's 10 hours from the beginning to the end. The equivalent in Germany is 30 hours. Speed is everything. Speed is everything for automotive. And you are right, you said that to respond to these Italian technologies adopted by Tesla, ArcelorMittal, you are right, are addressing new technology in steel, and they made recently an agreement with another Italian technology using only steel, avoiding and prohibiting aluminum in cars. Please go on the Arcelor website and you will see who is this company. Talk with your colleagues in ArcelorMittal.
Okay.
The steel is the answer. But to properly answer, you need to change completely the way a car is made. It has to be born electric, as a certain Pietro Perlo introduced in 2010, a contest that was later on copied by BMW later on. It has to be born in a completely different way. That's why ArcelorMittal now is returning to steel to respond to gigacasting. Okay, thank you. If you have comment on this, so lightweight is not an issue for these people, and they make very safe car with the highest ranking in crash test. Okay.
I don't know if my colleagues want to add something, and I only have to say that I agree partially with you. I agree partially because lightweight is not the key point. It's true, because if we are able to introduce better batteries, lightweight is not a problem. If we are able to have a bigger range with new batteries, new solid-state batteries or other batteries, lightweight is clear that is not a problem. But in any case, we are introducing new things in the car every day. So we have to be careful with this, because at the end, in electric vehicles, the weight is not so crucial. It is only a question of range, I repeat. But in any case, we have to be more careful with this. And I agree partially because I agree that steel will continue to be a good solution. So, as I mentioned in ALMA, we are not working with aluminium. We are not working with carbon fiber. We are not working with these materials. We work with steel, high-performance steel, sure, and SMC for some parts. So it's only from my part.
Okay, thank you.
Yeah.
Okay. It's actually we don't have time, so we need to carry on with the other presentations. To some extent, your question or comment already anticipated what we are going to have at the end with the final discussion. So let's, if you have questions, please ask questions about the presentation itself, and then at the end we will have the final discussion. Mr. Bein will be in charge of that, and we can come. You can have these kind of comments, and we can discuss about that.
Yes.
So-
Only one sorry, Enrique. Only one comment. If you are not able to talk today, my email is there, and obviously I would appreciate your comments or your emails. Thank you.
Okay. Thank you very much, Ms. Ledo. So we are going to move now to the next presentation. So Mr. Yakchi. So we are going to hear about Project Revolution. So please come to the, yes. So our next speaker is Mr. Yakchi Yavuz Emre. He's a research and development manager at Farplas in Turkey. So thank you very much for being here with us, especially considering what's the difficult situation you're facing at home. So thank you for being here. So he's going to talk about Project Revolution. The floor is yours. Thank you.
Thank you. So I would like to start with thank you to all the countries who have supported Turkey because of the devastating hurricane we had, just like how we proceed in the EU projects. We had a lot of support from Europe, and the country is trying to heal up. So Revolution is our project. Farplas is the coordinator. I might know a little bit more than the rest of the consortium, especially for the beginning of the project. We had some shop floor questions that contributed to build the project idea with the other partners. So just like we need electrical vehicles, and we need to make them lighter, all for the carbon footprint and for a more sustainable world. We had to speed up and make the preparations for the circular economy. But to our knowledge, in the shop floor, we knew recycled materials were not so easy to use, especially for the challenging parts like structural parts, aesthetical parts, lightweight parts. So we came up with the idea, why don't we prepare a whole consortium from cradle to cradle approach and target these solutions. Project is about supporting the electrical vehicle revolution through maximizing EV range and end-of-life vehicle recovery through optimization of recycled plastics and advanced light materials. Oops. Okay. Okay. The consortium exists of OEMs, injection molders, tier ones like we are, research institutes on topics like analysis, material development, AI, and special additives manufacturers. I like the way that this consortium is built, because more or less each partner is contributing in parallel without waiting the other ones to complete the task and then starting their own. All the progress in the Revolution project is more or less shared by the partners equally. So we are the coordinator and some information about the budget and everything. One thing I would like to emphasize is except for one thermoform case, the production method is injection molding here and prepare materials to be used in injection molding and using artificial intelligence to optimize the input of recycled materials so the target is to achieve 10 to 40% lightweight part-wise, and while selecting the parts, the consortium cared these should be a family to represent a bigger share on the car, and the final lightweight potential could be a lot bigger that can be than that is represented on each part. And also, just like I mentioned, the circularity potential should be high, and in each part we try to implement circularity and recycled materials. So the parts are back seat panel, B-pillar cover, crash box, and lower rear bumper. These are aesthetical parts, structural parts, body parts. We thought when we do this, achieve those lightweight potentials with circular material, with introducing the right methodology to produce the materials and to process them while measuring anything during all the processes, all the technical data will help us to bring the solution to the injection molding related automotive world. So our target is, as mentioned in here, lightweighting, superior performance, and end-of-life advantages. Implementation is proceeding as mentioned in here. Optimization of lightweight material, development of advanced process control, modeling and design, demonstration, and validation. This is how materials and energy in automotive should not be benefited. How we introduce in Revolution is the cradle-to-cradle approach, where circular materials are brought back to the production. Two cases are used here. One is mechanically recycled materials are used in the parts. In the other case, also polymers are brought back to the monomer phase, and also polymerization is occurring to make this automotive polymers. So in a wider explanation, these are the parts that we target in the project. The rear back seat panel. There we use self-reinforced polyolefins, and the polymer itself is used to make fibers and the polymer matrix. There, again, from PCR content, there thermoform is used, thermoforming is used, and backseat panel is going to be manufactured. The other two parts are B-pillar cover, which is an aesthetical part. It's made of PMMA. It's quite challenging to recycle PMMA. And also it's quite challenging to make a lightweight part of PMMAs. So design is a critical approach here to achieve the lightweight target. The last two parts are in our plant, actually, are going to be demonstrated in our plant, the crash box and the lower rear bumper. A crash box is a metal replacement part. Then Tofaş, Fiat, now Stellantis will test the part. And one of the classical, most known approaches of lightweighting technology, metal replacement is being used here. And our partners like VTT and Basel have introduced new material families to achieve this part. And the last part is the lower rear bumper. We will use chemical foaming technology in this part. Farplus is used to make plastic parts even lighter. There you either use low density materials or use microcellular or chemical foaming kind of technologies. Here we will use these. At this stage of this project, all material categories have been produced, and the tests, the FEA finite element analysis tests have been made, and the materials seem to be production ready at the moment. We will proceed with tool development. Of course, the part design has followed in cooperation with material design, and the tool development is following at the moment. And in very near future, we will produce the parts and see whether we have reached our targets that have been calculated in the simulations. So part design is not the only simulation we make for this project. One other really important approach is the process design. Farplus is one of the partners that contributes this project with data and AI, just like IDENER and VTT partners. Before this project, we already had a big data system in our plant, and we were trying to understand the relation in between quality measures and process parameters by collecting data from the production. There we could find some methods that contribute to quality issues, but without one fact. We were thinking, we were thinking everything is okay, even the material properties are okay. What if we use circular materials, recycled materials for our lightweight parts? What if properties change during the production? We assume material providers will send us constant quality, constant property materials. What if this doesn't work like that, or we work with a broader range of material providers. How we make a production line ready for fluctuating properties. That's why this project is quite important. During the material production, partners like VTT and Basel are working hard for circular material with constant properties, but also in our plant, with the support of our AI partner IDENAR, we work on an intelligent line that can process circular materials, maybe with fluctuation properties, in order to get constant quality parts all the time. So this AI pipeline works for this, and the models have been implemented already. Now we are building new sensors to especially to measure the flow nature of the material during the production, because flow is quite crucial for injection molding. Imagining polymer chains might be broken to shorter ones, or there might be still some longer ones. Your material can flow fast or slow during from shot to shot, so we want to control this. Even though this is a lightweight call, we knew circularity is an approach for the same aim. That's why we made an intelligent line for this project. Okay, I'm about to finish soon. So the process modeling has been made, material modeling has been made, and component modeling has been made during the work package 3 for all components, material and processes. And for our project parts like crash box, bumper, especially for the crash box and bumper, the process modeling and part modeling has taken a lot of work and time. So objectives for demonstration and validation are obtain lightweight with circular design approaches with advanced materials, evaluate EV range advantages with all demonstrations, structural part sensor applications. Not only we want to control the material production and the process, just like the projects mentioned before my talk, we will have sensors on the parts and see how circular material proceeds in its lifetime, in its work time on the car. We will measure this. This is going to be measured via tensile strength in between faces of the material. Sometimes you could say in between measuring happenings in between fibers and polymers and minerals and polymer chains itself. These sensors will measure how the part is taking the stress during its lifetime. Our approach is cradle to cradle, since all actors, all partners are trying to make a value together, from raw material back to raw material, manufacturing and use itself. This is our approach. Yes, that's all. Thanks for attention.
Okay, thank you very much, Mr. Iacci. We have time for a very quick question. There. Thank you.
First of all, congratulations for these really ambitious targets. Lightweighting up to 40%, plus 8% recycling materials. I think this is really, really challenging. So my question would be, we have national projects, we have used packaging materials for olefins, for recycling materials in automotive. And if we are happy and really have addressing new materials, new compounding methods, we achieved less deterioration of 5 to 10% compared to virgin material. And this is a short-term package material. And if you look on your end of life, 12, 20 years, materials coming back, you have fatigue, and how you will achieve your technical level plus 40% lightweighting. This is my question.
Yes, this 40 and 80 was written during the proposal part-wise. Of course, if anyone can make the whole car 40% lighter, it's going to be a real challenge. Structural lightweighting and chemical foaming can reach up to those levels. We had a battery carrier project from metal to plastic in the past. The part could be reduced to half with composites. I think a crash box in our case has potential. It's a metal replacement, and also chemical foaming in Farplus. We have examples of 30% lightweighting. There comes the question that recycled materials during their lifetimes are becoming weaker, and it's hard to use them in this kind of lightweight challenges. That's the purpose of our project. If needed, to fix the polymers with maybe chain extenders, with other additives, and make them fresh again, measure what's happening during compounding, even introduce some additives during injection molding, engineering additives. So I agree with the concern, but this is also our target.
Okay. Time-wise, we need to stop.
Okay.
Thank you for the question and the answer. So thank you very much for the presentation as well. So we're now going to move to the next presentation, which is about Project LEVIS. So Ms. Lazar, if you can come to the stage. So Ms. Lazar is a FEM engineer at Itainova in Spain, and she's going to present Project LEVIS for us. Thank you.
Okay, so thank you for the presentation. My name is Clara Valero. I work at Itainova. We are the project coordinators of LEVIS, which aims for advanced light materials for sustainable electrical vehicles by integration of eco-design and circular economy strategies. So first of all, we have some information about the project. That's the topic under it was granted as the sister projects that are being presented in this session. LEVIS is also a 3-year project. We have just started our last year. And well, we Itainova are the project coordinator, and the whole consortium is formed by 13 partners. 8 of us are research or technical organizations, and we have also 5 industrial partners that allows us to translate our results into the industry. And we are from 7 different countries around Europe. So the global objective of LEVIS is to develop, verify, and demonstrate lightweight components for electric vehicles by adopting eco and circular design concepts from the design phase to the end of life stage. So we are concerned about what happens with our components during their use and also after it. For that, we have selected 3 use cases: a suspension control arm, a battery holding set, which is divided into sub-cases, and a steering column carrier group of cross-car beam. The reason why we selected these 3 components is because they have different, or they are made of different materials with different manufacturing processes. They have different functions. So one of the specific objectives of LEVIS is to be able to replicate our results, or to use our materials and manufacturing processes in a higher number of components of the vehicle chassis and body. Obviously, another specific objective of our project is to obtain a relevant weight reduction in our components that will be later translated into the whole vehicle chassis and body, not the whole vehicle. Obviously, another important objective is to reduce production costs. As said before, there is no point on reducing, for example, weight if we don't reduce costs. We are also focused on obtaining high recycling or reusing rates of our components. And finally, we are concerned, or another specific objective of LEVIS is to reduce the global potential, the global warming potential at vehicle level. So now I will present you some of our results. So the first and most important result from the LEVIS project is are our new design of the demonstrators. So we have proposed different hybrid metal composite designs which are easily disassembled. So at the end of their life, we can separate, for example, the metals and the composites, and also we can later also treat these composites to obtain the sub-components. So those are the current designs. Most of them are frozen, and some of them will be very soon frozen. So we have our final designs, and we have estimated weight reduction around 35% at the component level, depending on the use case. And with the replicability study that we have performed, we have selected, or we have found to which other components that are not studied in LEVIS this reduction could be applied. So we estimate that we could obtain up to a 25% of the reduction in the chassis. Now I will present you briefly some results following different parts of our project, the most relevant ones. So the first one is the development of new bio-based, recyclable and recycled materials for electric vehicle components. In that concern, for example, we have developed a cost-effective bio-based carbon fiber to replace traditional commercial fibers. Also, with these bio-based fibers, we are able to speed up the production process, and the mechanical properties that we obtain are close to the target that was proposed initially. With these fibers, and also with standard commercial fibers, we have developed thermoplastic tapes. We have not found any equivalent product with the matrix that we have selected. We selected a thermoplastic matrix, so it's later will be easier to disassemble our components. We are also working on some components use short fiber composites, And in those cases, we are using specifically recycled carbon fibers, obtaining good results in our components. And also, as I've said before, we are also concerned about not only disassembled metals and composite, but also when we have a composite component that is not longer being used, we want to separate the constituents to manufacture new components with recycled fibers. So in this aspect, we are performing low temperature pyrolysis of the composites to obtain this, to separate the matrix and the fibers and later reuse them. Another important part of our project is that we are proposing hybrid designs to replace designs that traditionally were made by just one material. So as an example, we have a side beam in the battery box, which was initially made of aluminum, and in this case we have analyzed how we could improve or maintain their performance and reducing the weight. So we propose to reinforce the most critical zone with composite pads, which allows us to, for example, reduce the overall thickness of the profile. Also, in this line, we are working on different ways of improving the bonding between the different materials. We are working on, for example, on laser texturing of aluminum, which improves bonding and also gives good properties in terms of the strength of the joint. And also for the, as said before, for the disassembly of the different components, we are working on the development of a thermoplastic acrylic matrix, which is specially designed for our purpose. So we have created a new formulation of this matrix, so it has good mechanical properties and also good properties in terms of for the manufacturing, in terms of processability. And well, okay. Another part of our project is sensoring, which has been previously also mentioned in some projects. In this regard, we aim to include some sensors in our components, so we can monitor if they fail or their state at their end of life. So for that, we have manufactured different sensors on demand with different. We have tested different geometries, materials, sizes, and we are working on their integration during manufacturing in our components. With the information that we obtain from these sensors, we have developed some structural health monitoring systems. So with different active and passive techniques, we are able to monitor, depending on the component, different failures that may that could take place. For example, the bonding or the lamination in composites. So yeah, we obtain a lot of information from these sensors. In terms of sustainability, as I've said, we want to obtain high rates of recyclability and also of reuse of our components. So for that, we are working on the development of the bonding on demand structural adhesive, again especially designed for our purposes. So this is a commercial structural adhesive that it's been modified with particles that are thermally activated. So when we want to disassemble our components, we apply temperature and we obtain so far really good the bonding effectiveness. So we can easily separate the materials to reuse or to recycle or whatever we want to do with them. Also, we have developed an eco-design toolkit to integrate life cycle thinking and circular economy in the design process. So this is a tool that gives you some suggestions, advice, tips when you want to do a design. So you include this eco design perspective in your design. Finally, about dissemination, also we have done presentation in many conferences, we have written papers, but I would like to highlight the cross-project cooperation with the sister projects. As has been previously said, we have created the Enlight LEVIS cluster, so we can join our forces and communicate our results. We are also organizing an event with the Revolution project about sensoring. If any of you is interested on participating, you can ask me or my colleague if you want, and I will give you some information. And we have also presented 2 patents from the Mo2A, which is the battery box. I would like to finish with the impact of our project. As I've presented previously, the most, let's say, or one of the most important objectives of the project is to obtain a significant weight reduction. With our materials and manufacturing processes, we obtain lighter components. Also, we obtain, let's say, safer components, thanks to the structural health monitoring that can give us information about the state of the component and give some prediction about their remaining useful life. Another important point is the speed up of the production with some one-shot approaches that we have. I have not presented here today, but we have also developed them in the project. Also, we expect that with our advances, we will be able to reuse or recycle a high amount of the materials that we are using to manufacture our components. Yeah. So another important impact from our point of view is that all the developments that we are doing in LEVIS can be applied not only to the components that we have analyzed, but also to many other components in the automotive sector and also even in other sectors. Why not? So I'm talking about the manufacturing, dismantling, repairing, recycling, recovery, also the structural health monitoring techniques that we have developed. And finally, subsequent impact, let's say, is the reduction of the associated energy consumption and the recycling improvements that will lead to reduce the global warming potential of the components, which is, well, beneficial for everyone, I think. So that's all from my side. Thank you.
Thank you very much. We can take one question, if there is any, from the audience. No questions. There is one.
Yeah. So David Storer from CLEPA, the Association of Automotive Suppliers. My question is about the performance of bio-based carbon fibers, if the performance is equivalent to other carbon fibers.
Right now, as far as I know, I'm not. We are not manufacturing them. The properties are not at the same level, but quite close. And initially, in the proposal, we estimated. We knew that, so we estimated a a property level, and we have almost reached it. So right now it's not the same, but I guess it will be in, maybe not for LEVIS, but in the future.
What is the manufacturing route of the bio-based fibers? The
Sorry?
manufacturing route, what is the origin of the bio-based carbon fibers?
I think it's a cellulose precursor they use,
okay.
yeah. But I'm not the, the expert, so.
Okay, thank you very much. Thank you, Ms. Lazar. So let's move to the next presentation. So let me introduce the next speaker. So Mr. Bianchin Alvise, he's project manager at Matrice in Italy, and he's going to talk us about project FLAMINGo. So when you're ready.
Sorry, I know I will need it. Okay.
Yeah, you click on FLAMINGo.
Exactly.
Yeah, or
So I warn you, I didn't use the same template, but was not on purpose. So FLAMINGo is a fabrication of lightweight aluminum metal matrix composites and validation in green vehicles. As I said, my name is Alvise Bianchin. Matrice is the R&D branch of MBN Nanomaterialia. That is a company involved in the project for the coordination and also for the manufacturing of one of the key components, that is the nanoparticles. So the consortium, as you can see, is spread all over Europe. The project is of the same kind of the other presented today, but it is a bit longer. And all the partner has been collected together in order to have a good coverage of all the production processes that can deal with the aluminum metal matrix nanocomposites. So the metal alloying, the low pressure die casting, green sand casting, topology optimization, extrusion welding, non-destructive techniques for the material characterization, so the component characterization, and recycling. Then, of course, activities supporting the results, and in particular LCA standardization, and here not mentioned also nano safety assessment. So the objectives of the project are quite focused on the material itself. So we have the production of the nanoparticles additives via solid state mechanical alloying, their casting into billets through techniques like ultrasonication and stirring systems, and then the use of this in die casting, low pressure die casting, green sand casting, and extrusion to have the components. This is supported by activities on assessing the weldability of the material that we get out of this process, so weldability on the components, the topology optimization of the components itself in order to maximize the possibility to have a lightweight component, and the validation of the recycling of these materials using techniques that are already available by the companies that are doing already recycling of aluminum. The overall target is to obtain a material and components that can be valid for substitution of steel, particularly on electric vehicles. So the overall flow of activities and processes is this one. There is the initial manufacturing of these master batches. They use in foundry to have this cast that can be used for extrusion on die casting. the installation of the components in a vehicle, the actual use of the vehicle, and then the recycling. The field test is a part of the project that basically make this project to extend more than the other 4 that we have seen today. One important thing to notice is the fate of the nanoparticles and the role of recycling. So one of the core idea of this project is to follow the material evolution throughout all the value chain, all the supply chain, and to be sure that when it reaches to the market, when it reaches to its end of life, it can be treated as any other aluminum component, so without special regards about it. And in order to do that, we knew that nanoparticles has to be somehow removed from the cast eventually. And this also play a big role in the overall costing of the material. Since we are dealing with nanoparticles, there is also a good part of a nanosafety assessment, because we want to be sure to provide eventually all the guidelines, all the informations for the use of these materials in any stage of their value chain without any troubles. So at the moment, we are focusing on a couple of quite representative components from this vehicle produced by Eike, one of our partners, which are the steering knuckles and the rear frame. So these 2 parts here. The idea is then to do an extrapolation exercise once these components are validated, and once we have all the information on the mechanical properties of the material, to other vehicles and to the entire Eike vehicle, keeping in mind that the target for the cost is €3 for each kilogram saved, because these materials are not going to cost less than the current materials. So currently, we reached at component level a reduction in weight between 31 and 58% on the steering knuckle, and 35 on the extruded rear frame. The difference between these 2 numbers is strongly related with the technique for the casting. Yeah, I have an example here. This is the component, the original steel component, the topology optimized component in aluminum, and the actual component obtained after the casting. There are different techniques of casting. One that we are using in the project is the sand casting, in which the mold is quite flexible in terms of the design of the components. This allows to reach the maximum lightweighting possible. The low pressure die casting, on the other hand, needs to have a mold which is that puts some constraints on the design of the components, and therefore a lower overall weight reduction. We're not applying the same topology optimization on the extruded parts, of course, because for that wouldn't make much sense. But the FEM analysis on the current components utilized in the vehicle and the new one that has been designed for the extrusion die that is being used in these days, actually, will provide also for the extrusion part the same results. On top of those weight reductions, we are working in parallel on the material itself that allows an increase of mechanical properties, both on the alloy for casting and in the alloy for extrusion. There are a bunch of X's here because we tried different alloy compositions in order for, on one side, on one hand, to pick the best performing one. On the other hand, also to gain knowledge on how to transfer this concept of metal matrix nanocomposites onto different aluminum alloys. So I didn't introduce much the concept of metal matrix nanocomposite, but basically the idea is to have this additive that is rich in nanoparticles, can be used in the cast without giving to the casting company the problem to deal with direct handling there of nanoparticles. And these nanoparticles enter in the casts as a grain refiner, basically, improving the overall heat strength, tensile strength, reducing the elongation, and in some cases improving also the elastic module. These nanoparticles are introduced in order to be cost effective. We try different nanoparticles recipes, in keeping always in mind the target of the cost. For example, boron carbide nanoparticles were ruled out quite soon. Aluminum oxide nanoparticles were one of our favorite in terms of costs, but eventually resulted not in the best way performance to cost ratio. So in order to maximize the results, as said, we are performing this other set of activities, especially the aluminum recycling, with an actual company doing recycling of aluminum. The writing down of these guidelines for forming, assembling, and handling of the nanoparticles, always considering a nano safety. These are meant for increase the applicability of our results into by other companies, by other casting companies, extrusion companies, and of course the assessment of methodologies of the evaluation of new components. That is part of the non-destructive techniques activities that needs to be done on the final components and during the months in which the components will be used in service. So about the Enlight EV cluster of projects, this was something that has been initiated because we knew in all between our project there will be not a single winning solution for lightweighting electric vehicles, and possibly to have a platform in which to put together all the results in a single portfolio. So far, I think we successfully reached the possibility to do some activities, common activities on LCA, at least on the front of sharing our results together in a webinar. That can be also a first step forward to share something more like baselines for evaluation of the results. Ideally, we will have together the possibility to have stronger voices and bring evidences to technical committees on ISO. From our side, for example, the activity is more on recognizing the aluminum metal matrix nanocomposites as a material for the automotive industry. As regards impacts, in the short term, of course, there are impacts that are mainly related to the vehicle that we are currently targeting. So more off-road capabilities, more functions. This is an utility vehicle. Increase the working range of the fleet and enable more flexibility in vehicle configuration. These are all directly derived by substituting components with aluminum ones, lighter ones, and therefore increasing the overall range, basically. But on more medium-term impact, there could be the possibility of an overall redesign of the vehicle, in which the reduction of weight enabled by the use of aluminum metal matrix nanocomposites results in a reduced amount of battery, and possibly also a redesign of the entire vehicle engine system. This, of course, is something that our partner ALKE is looking as a medium-term impact of the project, but could be, of course, implemented by other car manufacturers in other vehicle sectors, and we are actually open for that. This, of course, is just the more evident impact, if you want, the tip of the iceberg. What lies behind is the possibility to establish wide guidelines for workers using nanoparticles enabled materials. That for us is very important to support the uptake in the market of this solution. Similarly, the guidelines for the recycling, we are not aiming to invent new way for recycle these materials, but just provide guidelines on how to use the already existing technologies by the aluminum recycler in order to deal with this material. Because of course, at the beginning, if these are on the market, there will be not enough aluminum metal matrix nanocomposite to be collected by their own and recycled by their own properly. So this guideline will be for improve the recycling capabilities of the current practices. The availability of wider portfolio of sustainable material is one of the main goal. The support of the inclusion of concept of nanoparticles in the current regulation and standards, especially in the market of automotive, and manufacturing guidelines for casting and welding. And this will be the main results for the uptake in the market of this material. And I think I covered all the parts. So thank you.
Thank you. Are there any questions?
If not, I have one. Can you elaborate a little bit more on the motivation for using aluminum metal matrix nanocomposites in comparison to conventional aluminum grades?
Yeah, well, this gives the possibility to increase the mechanical properties of the current available aluminum, and it is currently used by Constellium for their high strength line of aluminums. There are different mechanisms that increase the mechanical properties. One of the downside is the flexibility of the material, so it will be more rigid, but of course it is always a compromise. In general, it's nanoparticles are providing smaller grains in the crystal structures, and let's say point in which the dislocation are scattered and blocked.
So basically performance-based.
Performance-based, yes.
Thank you.
Maybe
one question.
Yes, one.
Hi, sorry, Frédéric Chausson from Strat Anticipation. I was just wondering, are the two, your project and the previous project, can they be combined?
Can? What?
Can they be combined? Because you're working on the aluminium, and the previous project also on aluminium. You're on the nanoparticles, you were on the plastic combined. So, just a question.
Yeah, indeed, they can be combined. We can have many different combinations between these projects. For example, with Fatigue4Light, we can have our materials validated by the methodology. And with ALMA, we can have our materials included in BESVIM. These topics are live in the cluster. And as regards the combination with multi-materials, yeah, probably is something that at the moment we are not focusing on, because the extrusion, well, we are not working with lamination of aluminum, and so it's a step that we lack in order to have a proper match. But on calculation can be done definitely. With the properties, the material card can be definitely used and see which is the overall combination of the two approaches.
Okay, good, thank you. Okay, so looking at the time, let's move to the next speaker, which is also the last presentation for today. So let me introduce you Mr. Aramburu Enric. He is Fluid Engineering Product Manager at IDIADA in Spain, and he's going to talk about Project Upscale.
Yeah, thank you for the introduction. Okay, let me try to link this presentation. You will realize it's a completely different topic, but links perfectly with what's been shown so far. You've been showing very interesting projects about new materials, even new processes, very different ones, very complex, I would say, also, okay? And now the question comes when, well, this has been in the frame of R&D projects, maybe 3 years, 3 years and a half, but when it comes to the real car development, a new real program, okay? So when it comes to this, the question is, do the engineering companies, the OEMs, have the right tools for decision-making, whether to use it, not use it, in which extent, and so on? But these development teams also are not facing only this, while introducing these complex materials, but also, there is a boom of projects. There is, simulation needs or decision-making needs are growing hugely, okay? So the question that was posed when the consortium started this project, or when we made the proposal, was, do we have the decision-making tools necessary for this, for what's coming? And the question is also now, for the future, do we have this available for speeding up the projects, for doing, you know, when you follow the news, the number of new EV programs and projects for each brand is huge, okay? Do the tools that we had at the time that we have, which are typically finite element, CFD, finite volume, etc., okay, can deal with this? Can we accelerate this, okay? And that's the main question. So here we are, basically you are simulation people. Simulation people from OEMs, simulation people from software vendors, from engineering companies, and also experts in artificial intelligence. So that's about the project. It's about, can artificial intelligence help in this process? Can accelerate the development of cars? That's the summary of the project, okay? So back 5 years ago, we started from, let's say, quite blank page. We knew that in the academia, there were nice ideas, inspiring ideas to do so, and that could help in this process, okay? So we have been devoting 42 months to developing this framework for different applications, but with this objective, accelerating. Colleagues said today, time is very important, speed is very important, so accelerating the process of developing a car with these very complex new materials that are coming. But not only materials, we'll see later, when we're thinking about the challenges in efficiency, of course, rolling resistance is very important, weight is very important, but aerodynamics as well. So this project also focuses in these two applications. So in key figures, Upscale had the challenge to accelerate the simulation methods in several orders of magnitude, accelerate development, so typical program development in 20% of an EV, okay? And that's the key figure that we were afterwards measured for. So, and then we choose two applications. I anticipated a bit, aerodynamics is one, CFD is one, crash is the second one. And the reason for doing so is because these are the two disciplines that are requiring more computational resources. So here's where we have more potential to reduce simulation times, okay? And well, here I try to explain what we did. So we'll show next the results, of course, all the results, but I'm taking a bit more time in showing the motivation and the object of the project. So traditionally, we have been doing what Mr. Einstein is doing. We simulate the physics. We go from the physics. When we do a crash, we know the laws of the physics that we need to solve in that structural problem. And in the end, we end up with a big equation system that we need to solve. So that what we are solving by finite element works very well. We have been doing this for 30 years, okay? But let me tell you also, in these last 30 years, there have not been really breakthroughs in this. This theory was developed before the computers came, applied when we had the computers available, and we're still doing the same. We do this very well. The results are very good, but it's not fast. For a crash or for a CFD, typically, you may need maybe one overnight run in order to get the results. So we want to improve this. And the way to improve this is by introducing artificial intelligence. Artificial intelligence is completely different. It's all the way around. We are not really solving the physics, but it's very fast. In the end, artificial intelligence is a, let's say, well, as its name says, it creates some polynomials that are very easy to compute, okay? That's why it's so quick. It's only solving linear algebra. So after this training process, what the training process means is that we are creating kind of polynomial that's self-created, okay? So when we get this polynomial, we will get the solution. That's why it's extremely fast. And it's happening a bit what happened with finite element also, that this is accelerated because now the computers are much and much more capable. And in difference also of the finite element method, artificial intelligence and machine learning, it's much more open. It has a lot of methods, much more versatile, much more flexible, and here is where the research comes, in which methods we use and how we use it. In the end, we apply one method, it self-learns, it self-creates the polynomials, and we just push the button and get the result. That's extremely fast. Let me go already to the results. We applied this to two fields. First to aerodynamics, second to crash. In the field of aerodynamics, we had a dream. Instead of having an overnight run, or maybe 5-hour run, 6-hour run, we want to get the result, the aerodynamic forces in seconds, or in less than 1 second, okay? That's our dream. So for doing so, what we figured out in the consortium was, if we have a new shape, we want to know the aerodynamic force on that shape. If we can parameterize this shape in order to get kind of digital signature of the shape, a mask of the shape, okay? In the end, if we can represent the shape by a very limited number of figures, for instance, 15, 20 figures, okay? We can link the result to this. So we get a lot of data of the aerodynamic forces on very different body modifications, and we populate a database with this, and then we apply machine learning, and we have the machine learning model. That's the idea, okay? But for doing so, we need to create a lot of data. We need to pre-run a lot of simulations. We need to generate these simulations in this. If you don't have the data before, you need to generate them, okay? So first, we need to parameterize the model and modify to generate a lot of variants of this model. For doing so, we use what we call the geometrical parameterization. So we just morph the vehicle based, and we know which dimensions have been modified, okay? So that's the characterization of our vehicle. And with this data, we populate the database and we train the model. But that's not enough, because in this case, you always need this to modify this shape in the same way by modifying the dimensions. But what if a designer modifies by his own, with kind of morphing tool, or maybe just by clay, typically clay model, where you just scan the model, well, you get a new shape. And we want to characterize, to reduce this at this mask, okay? So we need to develop what we call universal parameterization method that reduces a shape to a very limited number of data, okay? In this case, we are showing an example of this, that this is for the 2D, but it reduced that definition of the vehicle to 13 values, okay? When we did for 3D, could be done in 17, less than 20 values. So when we have a completely new shape, this can be represented by 10 numbers, okay? So this is the definition of our new shape, okay? So that's, well, we are using this autoencoder technique, that's a machine learning technique that allows to do this, okay? So we need this, we developed this in the frame of this project. And then what we did is generate this design of experiments. In this case, we took one of the vehicles, we get 1,000 different variants of the vehicle, and we got the results in CFD, we got the aerodynamic forces, and we got the airflow maps around, okay? We drop all this into the machine learning. In this case, well, different techniques were tried, and then, well, as you can see here, we are getting very similar flow maps to what was introduced. So these velocity maps, pressure maps in the flow, in the air, are re-achieved with an error of less than 2%. And then the aerodynamic forces. That's the same. We have all these variants with the aerodynamic forces. We drop this into the system, we train this, and when we recompute, we can get the aerodynamic forces in 1 second, okay? And then here we fulfill the dream of our designers, because our designers want to basically modify the shape and at the very same moment know if the aerodynamics is being improved or it's worst, okay? So, and we can achieve this with an average error of 0.65%. So that's very good, okay? So that's the first challenge achieved in this project. We can get the aerodynamic forces in real time. So that's an example of using artificial intelligence, machine learning, to solve the, well, the flow field and the aerodynamic forces. And then I go to the next block, which, sorry, no, I was not finished here. We introduce machine learning for other applications. Also, still in the field of CFD, we improved the, you know, we have had to run 1,000 simulations, okay? That's extremely costly. So we had also the goal of improving the traditional CFD process, which includes different steps, the meshing, the simulation, the post-processing, and so on. We introduced machine learning in some key steps, in the meshing, in the initialization of the simulation. So with this technique, we look at the former simulations, we look which one is closer to the new shape, and we map these flow fields on this simulation, adapting perfectly to the new shape, okay? So that's a perfect starting point. That's a key technique. Then the volume measure was extremely also accelerated, and then also the solver. In the end, we reduced the simulation time from 5 hours in this case to half an hour for the whole process, volume meshing, simulation, and extracting the results. So that's a second application of the machine learning. Third application is still in the field of CFD. What I was showing before, these 5 hours to 0.5 hours, is with a bit simplified approach that's called Reynolds average Navier-Stokes CFD solution. Basically, what we do, you know, in flow, the natural feature is really chaotic. You will have the turbulence that's really hard to model. Indeed, it's impossible. So typical technique is averaging these fluctuations, okay? And then the solver needs to make some assumptions, some simplifications to compute the whole system, assuming that in some zones there are these fluctuations, okay? That's where we introduce more error. So we had an idea that we have a different approach that's what we call high fidelity simulations, where we simulate all the vortex and all the fluctuations and so on. And we had the idea that what we were missing in the simplified approach, that basically it's the computation at what's called so far Reynolds stresses, depended on some variables in this high fidelity. So we tried to learn to get patterns out of this to be used in the basically in the end improving the accuracy of these simplified CFD simulations. So that's the third application in CFD. And finally, well, the second block, the application to crash, which is maybe more close to the audience today. A lot of structural analysis people can be here. The challenge that we had, it's really a challenge. It's simulating a crash with a battery pack with all the battery cells and being able to predict short circuit in any battery, in any cell inside the battery, okay? So far, this was not possible back in 2018. And why it's not possible? Because you can see here, these are all the layers that you will find in a single cell. So only one cell, you can find thousands in a battery pack, only one cell could be, I don't know, 5 million, 8 million finite elements, okay? If we sum up everything, that's you need one century to simulate this, okay? So that was not feasible. And here is where it comes the machine learning approach. We used what it's called so far reduced order models. And basically, what we do is we try different techniques, but in the end, the most successful one, which has been developed by ESI Group, is using, now it's appearing a name that's constitutive-less material cards. Basically, is using a material card that learns from, let's say, micro or meso models, okay? Our meso model is what we are showing up. So we simulate one of these with many different load cases. With these results, this machine learning tool creates the material card for the cell, which is an isotropic material card that links with this. Okay, so can link can learn from all this. Okay, and then you can introduce this in the overall crash simulation. Okay, not only being able to simulate the deformations, but also looking at another variable, that's the risk of short circuit. This was introduced and tested and finally used by 2 OEMs in the project, in this case Volkswagen and Fiat. And in the end, the result is shown here. We can, well, in this, let's say, very challenging, we had really to apply very extreme load cases with this pole penetration in order to test it. But in the end, the result is, yes, this was implemented, this computes, and this can be used afterwards, okay? So here it comes the end of my results, okay, explanation. And here, well, a couple of slides about the summary, okay? Yeah, 2 slides. Thank you. Well, first conclusion is that we have been successful in this. This is implemented with different levels of TRL. Okay, I can explain a bit why, and for each of the topics. Basically, in the case of crash, this can be used already by companies, but needs kind of customization, special support from the software vendor. So it's not available when you buy the software already. It's kind of beta version and can be done. Same for the CFD accelerated process. In this case, there is a software vendor here. It's called Engis. If you use their software, most of this accelerated CFD process is included. Okay. In the case of turbulence modeling, it was just an approach, but we are still far from closing the process. And real crash prediction, real aerodynamics prediction, it's already a possibility, and we are not the only ones. When we started, this was completely new. We know that there are several companies here already doing this. The problem is linking this with the design process. So linking what we have been doing so far with the design tool, so that you can read directly the design tool and then get the aerodynamic forces. And I wanted just to finish by commenting a bit on what are the limitations of what we have seen so far. There are also some I would say, some drawbacks or some limitations to introduce this in the future for the community. Okay, data generation can be extremely costing. And this can be limiting very much. So if we, in any case, for instance, for aerodynamics, we need to generate 1,000 CFD simulations for afterwards computing very quickly, maybe it's not worth. It's better to use as a standard, because otherwise, first you have been devoted, I don't know, 2 months in generating cases and cases and cases. So that's we don't like this, okay? And the second point is because of this. The solution is restricted to what we have. So in the end, this is kind of knowledge management, but it's not guessing out of this design space. That's one of the problems and of the areas of research for the future, okay? So in the end, these are the limitations, and we figure out some key areas where we can work to progress with this, okay? Hybrid technology, I forgot commenting on a very important point. We are losing the link with the reality here, with the physics, okay? And this could be, well, something that people don't like. So we need always to correlate, validate, and so on. So here's where this hybrid approach, mixing machine learning with traditional CAE, traditional FEM, traditional CFD, is where it works well and is one of the trends. Finally, continuous machine learning, in order to, well, we had this 1,000, but if we, for the next vehicle, we can take advantage of this, that's very important, being able to apply these techniques. And finally, this constitutive-less material cards, I think, is here, and this will be applied for the future in applications like the ones that have been shown so far today. Sorry for the time.
Thank you very much, Mr. Aramburu. We don't have time to take questions now, so I'm going to give the floor now to Mr. Bein for the final discussion, and then if there is time for questions for you and for concerning Project Upscale, maybe we can do it at the
I
end.
asked the presenter to sit in the front. Yeah, so we allowed already a question to the presentation, so now the remaining 20 minutes we would like to dedicate to overall discussion on what we have learned today. So first I would like to give you the chance to ask questions to the presenters. Are there further questions? David.
Okay, so David Storer again from CLEVA. So yeah, referring to the different projects, particularly the ALMA project and the LEVIS project, It's very interesting, this interaction between lightweighting and recyclability, sustainability in general. Yeah, and it was, I heard very clearly the mentioning of the adhesives, structural adhesives to join different materials, which could be a very good option for the future, and the fact that they can be debonded through temperature, and also the recycling of the composite materials in the LEVIS project is very interesting. I have a specific question on the use of materials that are steel and plastic that I think was mentioned in the ALMA project, and also you mentioned about glass fiber. Do they pose any challenges when it comes to recycling?
Who wants to answer? Can you speak in the microphone, please?
Yeah, it's working. Okay. From ALMA project, as you mentioned, our focus is on disassembly at the end of the life, and we are thinking of disassembling different components. One component from steel and other component for about SMC material. But it's true that there are one of the steels that is developing at this moment is one sandwich. This sandwich is steel, plastic, and steel. And they are also working in the fact of disassembly at the end of life. The adhesive they are using at this moment is not the same that we are using for the joining of components, but it's true that the idea is that at the end of the life we can disassemble this sandwich and separate the two types of materials. It's clear. Thank you.
Further questions? Maybe I can step in here. It goes to all of the projects. So what are basically the lessons learned from your project in terms of circular economy? So in many of the cases you look focusing on disassembly. Only I think it was in the Revolution project where you also looked into secondary material resources. But what are the challenges basically in the multi-material design in terms of closed loop versus open loop circular economy strategies? What are the lessons learned from your projects? Who wants to start?
I start again. From our vision, the lesson is, the main lesson is that there are many technologies available today for recycling the materials, but you have to determine the type of material. So there are solutions for steel, there are solutions for aluminium, there are solutions for plastics, there are solutions for other designs, but at the end, the big problem is that we are not able to separate of these materials. So this is the main reason why we are focused on disassembly, because we think that the technologies are there, but we have to be sure that we can separate all the materials.
So is it the tendency to go for a lesser variation of materials to allow a better recycling? And what about open versus closed loop?
We are open to multi-material, but we have to be sure that we can separate at the end of the life.
But what are you doing then with the materials at the end of the life? That is also the point.
It depends. It depends. If we are able to reuse, we can reuse, and if not, we should be recycled. It's clear.
Maybe Clara?
Yeah, in our case, what are we doing with the materials once that we, for example, separate the matrix and the fibers in a composite? We are going to remanufacture new components, and we are going to test them to see the differences between the original ones and the recycled ones. Especially, we are going to reuse the fibers, as far as I know.
Do you see differences in the quality of the materials than what you are going to reuse? So the quality of the secondary materials has a strong impact on the design and on the manufacturing route.
We have not yet started this phase because it's the last one. Once we decide the design or the component that we are going to remanufacture, we will start this stage, but we are not on that point right now.
And maybe Alvis, regarding you indicated in your presentation you're working with nanoparticles. What is then the challenge regarding nanoparticles when you're going to recycle the metal matrix composite?
Actually, as regard nanoparticle recycling, we gave up immediately. So we knew it was not possible to have something effective on recycling the nanoparticles, but that is around 1% of the overall alloy. On the other hand, the aluminum recycling is fundamental. Doesn't make much sense to substitute steel with aluminum if the aluminum is not recycled. So from an LCA point of view.
So you need to recycle the metal matrix composite back into metal matrix?
Back into aluminum.
Directly back into aluminum?
Yeah. Okay. So that's the only way we can be sure that our material can reach into the market.
Yeah.
The idea as regards separation of different components, separation of different aluminums, and the quality of aluminums is really connected with the kind of alloy that you want to use in the car. And I think our approach is compliant within a possible future trends into reducing the number of alloys into possibly just one. And
okay, there were, I think first in the back, Andrea.
Because we cannot see you then on the recording.
Oh, sorry.
Not a question, but just an information. I mean, as the participants of this session are interested in transnational R&D projects in lightweighting, I wanted to draw your attention that there are funding schemes even beyond Horizon Europe. I'm Andreas Storder from the Austrian Ministry for Mobility, Energy, Environment, Innovation and Technology, so that's just a long title. We joined our forces among member states for a Eureka call, which will be finished on the 25th of April on all aspects of lightweighting research, including circular economy. And the member states participating are Spain, France, Sweden, Switzerland, both parts of Belgium, Flanders and Wallonia. And what might be especially interesting for you is that we even have partners outside Europe with an interesting industrial structure and supply industry and OEMs. These are Canada and South Korea. So if you are interested in these transnational R&D projects, funding, I will be ready in the break. Thank you.
Thank you, Andrea, for this hint on additional funding sources. But there were other questions in the audience. David.
Yeah. Is it working? Yeah. Okay, so I'd like to get back actually to the point that my esteemed friend Pietro Perlo made earlier about whether it's wise to follow Tesla in terms of making vehicles of stainless steel bodies with battery packs that weigh hundreds of kilograms and basically really expensive high performance vehicles that cost a lot, whether that's the model that we want to follow in Europe, whether we don't risk leaving a gaping hole in the market for cheaper, lighter, less expensive vehicles, that entry-level electric vehicles. So yeah, that's a little bit the question. Where are we going in terms of weight reduction? Because we see small changes in terms of aluminium knuckles that are reducing the weight by a few kilos, and at the same time electric vehicles are now weighing 2.5 tons if you count the battery pack and everything. So I just wondered a little bit how we are going to in some way find a solution and make sure that the market is well covered by European manufacturers, rather than allowing a hole for an opportunity, let's say, for players from other countries, other regions around the world.
I think this is a challenge already addressed by Pietro, but it would be really indeed interesting to hear your opinion. It also linking to the additional challenges you see for lightweighting in the future. Who wants to answer?
Well, I'm a CFD guy, I'm a trader of lightweight and so on, but the thing is, if we go to 2.0 real, in the end, we need to, to improve the efficiency wherever we can. So I don't know which will be the milestones exactly, but will be, I think, kind of forced to be step by step improving it. But well, this is a very generic answer. Maybe my colleagues can answer more concretely.
There's in the lady for us.
Emma Briek from Green Innovation. Whatever we think about Tesla, Tesla is a good car, that's for sure. But lightweight is range. Whatever, we can put more batteries or put lightweight. If we have more money, and we can go for bigger battery and bigger, best chemistry, and we can also add some range by adding lightweight. This is my thinking.
But is it real?
It's question of cost. It's question I asked. I already put a question. It's question of cost, and the cost when we calculate it for lightweighting is based for what we earn in term for EVs in term of range. If the balance is good, so lightweighting is good. If not, we go for more batteries.
I would like to challenge this a little bit. It's not always about cost, it's also on environmental impact and resource sovereignty and so on. So we cannot avoid the physics. The more mass we are driving, the more electricity we need.
So it is also when we calculate the cost, the cost is not only batteries, but also the environmental impact.
Yeah.
It's an overall, you can check it with OEMs. When they calculate the cost, it's not only the impact on CO2 or for thermal cars or range, but also it's an overall calculation, taking into account LCA as well.
Yes.
And the recyclability. So whatever we think about Tesla, Tesla is a good car, that's for sure, but we can also work lightweighting for vehicle because of the environmental impact and because of less batteries and less impact on environment, because batteries is an impact, negative impact on environment.
Pietro, you can have the voice if you keep short.
The first meter will be very short. The last 2 hours I will compensate.
Yeah.
So you raised a very nice point regarding circular economy. And that's indeed the first thing that people should start. Okay. For every ton of rock, you can extract up to 60% of steel. Per every ton of rock, you can extract at the best 30% of aluminum. Per every ton of rock, you can extract 1 gram of gold. So please don't develop cars on gold from an environmental point of view. Okay, but that is the first point. Steel is the most recyclable, the most abundant metal on the earth. Clear? I really invite you to listen a very nice presentation from a French woman working on mining, Aurore Stéphane. Okay, she's making fantastic presentation on mining of metals, and there will be a revision of the presentation the day before tomorrow. Okay, so really worthwhile to look first, but steel is also the material that can be used to make everything lighter. Make it in aluminum, I will make it in steel lighter. Okay? Make it in aluminum, I will make it on steel more robust. That's the point. I am paid by the largest company on steel, and I am also paid by the largest companies on aluminum. But I am a super.
But still is
the material for future.
Still has
and
still
also cost.
Yeah. Yeah, okay. But the body in white is not the only part. I don't want to sit in a seat with steel. It's not comfortable. Steel is still the highest share of the material in the car. So definitely this will continue, but this not exclude that we have to follow lightweighting just to save energy and to become more efficient, and basically also then in terms of circular economy to keep the resources within Europe. But there was another question. Yeah, this one.
Carlos Amailek from Ficosa. What of the conclusions of what you've shown are applicable to copper or any other conductive parts? Because all it's about structural parts, but there's another chunk of the weight and especially of the cost related with conductive parts.
That's a good question. Someone covered this. Yeah.
No.
It's.
But this is not the focus of this topic, because this topic where FLAMINGo, Revolution, ALMA is working is about the body structure, is about the body in white. So we are not focused on the material you are mentioning.
Yeah.
Can you extract anything? Can you, I mean, but even though I know I'm talking about next steps of this research, can you extract or advance anything related with these parts? Thank you.
There are other projects ongoing, and there's in other areas like in the electronic part where you look also in copper and also in the recycling of the e-machine. There are possibilities. If you look into electronics, there are technologies and startups which can extract all the metals you would like to have at a very high purity. So there are technologies around. But we are coming to an end. We are scheduled until 12:15. So maybe we have one more question.
Trying to find a compromise. So we have the monomaterial approach and the multi-material approach. So, but I will come back on the idea of Raquel, I guess, to reduce the number of alloys. So in future, what we have done, we have produced a lot of 1,000 different materials, high strains, plastics, aluminium, casting alloys, with a goal of lightweighting. And now we are able to get not total back, but one step back, and have perhaps some very specific and harmonized materials. Do you think that would be an approach in future? Not to have 1,000 different of recipes of different materials, but to harmonize in some case the alloys, the recipes, in order to have a better recycling at the end.
I've given the example of single material composites. I think it's a good application, and the academia and industry should further focus on it. It's easy to recycle, and even though fibers and polymer matrices are there in the composites, it's basically the same material. Yeah, it's an example that I can give.
I think it's also a question of competition and business models of the material providers, right? And it's also then the demand of the end users, what they need. I'm not sure if we can harmonize on a big scale the different alloys, but it would be an interesting topic to discuss further. It's a pity that we only have no minutes. No, actually we have no minutes left. It's 12:15. So everyone is starving. At least I'm starving. I hope that you continue the discussion during lunchtime. I would like to thank the presenters for the interesting talks. And there were indeed
quite, let's say, encouraging what you achieved. And as you see from the discussion, it is also steering quite a lot of discussion. And I hope that we will be able to continue this discussion during the conference and also then later on. Thanks again for the presentation. Enjoy the lunch and have a nice afternoon.